This conference will now be recorded.
All right, so today we're going to cover two things. We're going to cover basin properties, and then we're going to go for a quick tour of the hydrology in SELDM. So this presentation goes over the geographic, physiographic, and anthropogenic or man-made basin properties that are used to specify storm flows. And I'm going to show you some example basins, and I'll talk a little bit about, how the properties that we have and how they might be used. Let's see. Whoops. All right, learning objectives. Again, we're just going to go through the different basin properties, discuss how they affect your model results. And you've seen this slide a couple times, is we have our storm event statistics. So our basin properties are for the upstream basin and the highway site. And basically, it controls how much precipitation, the area controls how much precipitation falls on the basin. The imperviousness controls the runoff coefficients, and the other hydraulic basin properties control the timing of runoff from each area. The first thing is the latitude and longitude. So we can see in this case, the first basin property is the location. When we put in a latitude and longitude, it's good to get for documentary purposes, if you're actually simulating a particular point, it's good to get a kind of an exact figure. Google Earth, the national map, or GIS on your phone if you're actually visiting the site is good. You can see here the rain zones are pretty big, and the ecoregions are basically discretized to 1/4 of a degree, so which is like a USGS quad sheet size. So if you're just doing a simulation in an area, you don't really need to be all that precise, within 1/4 of a degree. Or if you're just in this ecoregion, you can use maybe the center of the ecoregion. You don't necessarily have to get down to the site level. But again, if you're doing a particular site and the analysis is crucial, or is going to be in some regulatory sphere, it might be good to get a good value. The physiographic basin properties are the drainage area, the slope, and the main channel length. So in this case, we have a basin in map view, and it could either be the upstream basin or the highway site. The blue line here is the main channel going up to the basin divide. So the basin length is the length along the main channel. If it's wiggly, it will be the length of the wiggles all the way up to the basin divide. And the slope we use is the 1085 slope, which has been shown to be valuable for a number of flooding studies, where they're timing the hydrograph. And it's basically just points at 10% up and 85% up from the outlet of the channel. You just take the elevations off a map or out of GIS or the national map, or eyeball it on a map, and you just subtract the elevation at the 85 point. Well, you subtract the 10% point from the 85% point, and then divide by the length between them. And so those are your basic basin properties. The next basin property, it's the anthropogenic one, is just the total impervious area. So this is my representation of that basin with some roads and parking lots and roofs, etc. So the impervious area for the upstream basin would include all those. The impervious area for a highway site would be obviously the pavement. So the impervious area is used to calculate the runoff coefficients, and it can be used to calculate the timing of the upstream and the highway runoff hydrograph, which helps determine how much dilution that you might get. The next anthropogenic basin factor is the Basin Development Factor, which it's an index quantifying the prevalence of engineered drainage features. So it's curb and gutter streets, channel modifications like straightening, lining the channel with concrete, etc. How much storm sewers are in each third of the basin. It's not a hard number to come up with, but it's not easily automated. So you can use, instead of using the Basin Development Factor, you can use the imperviousness to get at the timing of the hydrograph. It's a lot easier. Using the Basin Development Factor gives you a slightly better answer, but with all the uncertainties in any model, that the difference probably isn't all that important. So when we're looking at basin properties, a SELDM site can be literal or conceptual. So a literal site would be, a particular highway with some, with a bridge over a stream, and that's what's draining to the stream. A conceptual site might be if you had several stream crossings, you might accumulate the different areas to one downstream crossing and kind of use some hydraulic variables that are representative of that site. A recent study, we looked at urban runoff using SELDM, and in that case, this diagram kind of shows how we do that. We have the upstream watershed, and the white rectangles here are the actual location of the urban areas, but we just took the area of the urban areas and some representative hydrologic characteristics. And so we just simulated them as if the upstream watershed minus the urban areas was contributing to the stream. So that would be more of a conceptual approach. And we'll talk about that a little bit later with some examples. So I said SELDM can be a literal site, so a bridge over a stream. So when we look at this, this is, I think it's I-95 over the Charles River in Massachusetts. So if we look at a literal site, we can look at each of these bridges contribute to the water quality in the stream. But if we think about it, what do we really care about? Do we really care about what's going on between these bridges, or literally what the regulators or we would care about is what's the net effect downstream? So we could literally model two bridges, or we can conceptually model the combined area of the two bridges and say that's one discharge to the stream. So the yellow lines would be the boundary of the contributing areas of the bridge to the stream. So if you have a bridge, the main channel length would be from the crown of the road to the scuppers, and there are no tributary channels. And then the slope of the flow line would be the 1085 slope between the crown of the road and the scuppers. Now, if these bridges had drain collection systems, then the length would be the length from the bridge deck down to the river. The slope, however, you wouldn't want to include any vertical sections in the slope because they don't really contribute to the timing of the hydrograph. It's more the more horizontal flow that contributes to the timing. Obviously, a bridge is 100% impervious. The Basin Development Factor is 12 because bridges are engineered to shed water as quickly as possible. But again, when we're looking at the timing of the hydrograph off the bridge, we can just use the imperviousness. So the next case would be, very often it's the bridge deck and some part of the approach that might drain to the stream. So this shows a topographic map with I-95. I think, again, it's crossing the Charles River. And what we see here as the yellow area would be the area of the two sides of the highway draining to the stream. So we're modeling two discharges here. The light blue line would be the trunk line sewer system that drains this area. The X's, again, tell us the point where we're going to simulate the 1085 slope. And these blue lines here, they might be tributary trunk line drainages to the main trunk line sewer. In this case, this site could be 15% impervious, and our Basin Development Factor would be 3. But again, probably using imperviousness instead of the Basin Development Factor would work better. typically what I suggest in these types of cases would be that you would simulate the 100% impervious area as the highway, and all this grassy median and shoulders would be your grassy swale BMP, if that's how the flow is routed. And our main, in that case, our main channel might be the length along the swale, the drainage length along the swale. So in reality, again, what we care about is downstream of this whole highway site. So what we would use is we'd use the area of both sides of the highway, and then we would use the length and slope of the side that's contributing the longest storm flow, because we're looking at the total time that the highway is contributing to the stream. So although this north side would drain quicker, we'd still be having storm flow from this southern side with the longer drainage and perhaps the lower slope. So this is kind of a conceptual site, because we're lumping these two discharges into one, because what we care about is the net effect of this entire site downstream on this river. Now, one challenging thing, but one thing that happens a lot, I think we have somebody in from Colorado, is in mountainous areas, you tend to get these highways that follow the valley up or down the stream. So in theory, you have many discharges. So this is a map of a stretch of State Route 16 along the Ellis River in New Hampshire. In this area, the river flows from the northwest, which is in the upper left corner, to the southeast, which is in the lower right corner of this diagram. The image on the right shows the same segment of highway that's been divided into 10 segments, each draining to an outfall, which is denoted by these perpendicular blue lines. The sites could be modeled individually, so we could model 10 sites to see what's going on. Or what we can do is we could lump the area to see the effect down here at 10. But then what we would want to do is pick some characteristic hydraulic effect, and that might be this drainage length shown in blue between number 4 and 5, and the slope that would control the drainage. And usually that might be the lowest slope, and the longest drainage length might control it. You wouldn't want to use the length of the highway from 1 to 10. You could use the area, but you don't want to use the length, because the water doesn't flow on the highway all the way from 1 to 10. It flows kind of down for a distance and then drains into the stream along the path. As we saw hopefully earlier, that you can easily set up an analysis, copy it multiple times, and set up different highway sites. So it's fairly easy to just set up basic runs without going into all the different water quality constituents, and just look at the dilution factor from 1 to 10. And you might want to say, well, what happens to the stream at the downstream at number 10? But what's the kind of the critical crossing where would stream flow be lower and the proportional highway runoff being higher, which is the dilution factor, to see what might be the critical point along the stream that's got the worst ratio of highway runoff to receiving water. So this would be, you can either model these as 10 literal sites, or you could model it as one kind of hypothetical site using these representative conditions. This is an example where you could model the pre-highway condition. In this case, SELDM can be used to model the pre-development condition. So in this case, let's say this tributary area is in yellow. So that's our boundary would define our area. Our main channel might be part an ephemeral channel, perennial or intermittent and perennial, but it's the main channel up to the drainage divide. And then the X's here would be our 1085 slope. I probably could have done a slightly better job placing these X's to look more like the 1085. We have our slope. Because it's completely forested, we have an impervious area of 0, and our basin development factor would be 0. So in this case, this might be the before condition, and then you're going to put a highway across here. That would be the after condition. The other thing that you can do is if there's a water quality, there's actually a highway here, and there's a water quality problem downstream of the highway, you can use the imperviousness of 0. You can use some forest runoff water quality, and you could show that perhaps the highway isn't the water quality problem, it's what's going on upstream by using some representative upstream water quality. Now that may not be far-fetched, as you guys saw earlier when we went through the case study with Howard Brook. Even though it was 6 acres of highway and only 1.34 square miles of Howard Brook, based on regional water quality, the highway had really no effect on the water quality in the stream because, total phosphorus because of natural soils in our area is pretty high in the receiving waters. So again, this is a case of you could do before and after if you're building a highway here, or if there's an existing highway and you guys are getting tagged as the water quality problem, you can use SELDM to demonstrate that perhaps the highway isn't a problem in this area. Or you might find out that it is, and then you could simulate different BMPs to say, what can the highway do to reduce the risk of adverse effects at this site if the highway is a substantial contributor. All right, parking lots represent about 25% of the total impervious developed areas in developed areas, and the state DOTs may own park and ride lots and whatnot, and they might have to worry about discharge from such sites. So again, because SELDM is this lump parameter type model, we can simulate what's going on with a highway, with a parking lot. So again, these blue lines are side tributaries. The light blue line would be the trunk line drainage system, the main channel. So we get the length of that trunk line drainage system up to the drainage divide. We'd get points that are 10 and 85% up that light blue line to get our slope. We can see there's kind of an island in the middle and some tree islands, so our highway might be 90% impervious. And in this case, within this little L, you can see there's some kind of retention pond there, so we could simulate that retention before it goes into the stream. So using these simple basin properties, we can simulate different types of sites. So here's a neighborhood. If you're looking at different contributing areas within your watershed, we can look at a neighborhood. So, again, the yellow line would be the outline. The light blue line would be the main trunk line sewer system or the main drainage from this neighborhood. The neighborhood is 30% impervious, so there'd be less runoff per, unit rainfall. In this case, the Basin Development Factor is 12 if there's a sewer system with drop inlets and, concrete sewers. And with some urban or neighborhood water quality, this imperviousness, this area, this slope, we could generate, what's the contribution of this site. Now, we don't typically look at neighborhoods, but there's a number of SELDM studies on our website where we look at the contributions of the highway and contributions of other developed areas to kind of see what the relative contribution is. Often we find that because the highway is such a small area compared to the large developed area in the watersheds where it exists, that, for TMDL purposes, the highway is usually like a trivial source. And SELDM also may be used to, model storm flow. In this case, this is a mall on Route 9 in Massachusetts. We could see it drains into this lake, which is, you can see all this mat of vegetation, so there's eutrophication going on. So here's our mall. We have our main channel, again, going from the drainage up to the drainage divide, the highest point. And then our 1085 slope would be in the main channel, or, in the trunk line drainage system. Now we can see there's roof drains and identified as other tributaries feeding the trunk line. We don't want to have these large slopes that might be artifacts of, having a roof drain. So you typically not include those vertical drops because they're almost instantaneous. You would kind of go with the semi-horizontal sewer pipe. So again, we can see a few tree islands in this site, and we So it's about 99% impervious. And because it has these sewer systems and drop inlets and it's designed to get rid of the water as fast as possible, that, the Basin Development Factor here would be a 12. So again, we do some urban water quality. We have this 99% imperviousness, these basin properties, and we could simulate what's the contribution of this site coming into this lake here. So SELDM can also be used to model storm flows from highway maintenance facilities. So in this case, here's a maintenance facility. I guess at the risk of getting too repetitive, we have our drainage area of the maintenance facility. We can see that it's about 70% impervious. We could see all these blue side drainage features, but we're looking for that main channel up, the trunk line drainage, or if there's this big swale going through this site. We look for that 1085 slope. And then we'd want, some water quality from, highway maintenance facilities to look at it. In the absence of that, we could probably look at kind of maybe more industrial urban runoff if there isn't a lot of highway maintenance facility data available. So when we get these simple basin properties, we specify them for the highway on the highway form. So this is the, I should jump back a little bit and say, this is the flow chart for the graphical user interface in SELDM. So we have the 3 documentation forms. When we went through SELDM, it was the analyst, the project, the analysis. Then we come to the highway site where we put in the latitude and longitude. And then the highway basin properties, we get the GIS grid. The latitude and longitude gives us our ecoregion. Then we put in our upstream basin information on this form. If we're doing a lake basin, we put that information there. And then we go through the hydrology, water quality, BMP forms, and run SELDM. So this is the highway site. Hopefully you recognize it from our run through the other day. So we have our short name, which is required because as you put in a highway site, your choices are up here. You could put in a full name, which is like 250 characters. You have your latitude and your longitude. In the Western Hemisphere, the longitudes have to be negative. So again, our hydraulics of the drainage area, drainage length in feet, mean basin slope in feet per mile, impervious fraction, and our basin development factor. So this highway site, we simulated it as the pavement and the grassy swales and median because, all the water's routed through these swales. And so in this case, we just chose to represent the whole site as the highway site, in which case you want to use water quality that's reflective of a highway and, with grassy areas. You wouldn't want to use pavement runoff for this whole site. And in this case, our basin development factor is 6 because there's a combination of, there are some storm sewer links and drop inlets. But again, SELDM has a cheat code. If you put in -1 here, cheat codes, what kids use on video games to make their life easier. If you put in a -1, it just uses the impervious fraction for the timing of the highway hydrograph. So for the upstream basin properties, it's the same thing, except the drainage area is in square miles, the drainage length again in feet, mean basin slope in feet per mile, impervious fraction. In this case, it was a natural basin, so the impervious for the basin development factor was 0. So this presentation is an overview. If you want to really dig into the details, we have the Federal Highway Hydrology report. We have our basin lag time USGS report, and then the SELDM manual kind of is an executive summary of these 2 reports. So it boils down the information that you need. So again, what we looked at was the latitude and longitude are the geographic basin properties. The latitude and longitude gives you your precipitation statistics, your streamflow statistics, and some water quality statistics that are all calculated and put into the model. The drainage area, main channel length, mean basin slope are the physiographic basin properties. So the drainage area controls, how much rain falls on the basin. The imperviousness controls the runoff, and the main channel length and mean basin slope help control the timing of the runoff. The total impervious fraction gives you your runoff coefficients and perhaps the timing of runoff. So the highway site and the upstream basin form are used to enter these basin properties, and they're just these very simple basin properties. They're fairly easy to generate, especially nowadays where we have stream stats and Google Earth to do these kind of tasks. You can do a lot of it without any GIS skills. And you can always, get out a map and pencil, and that's how these basin properties were done for the flood studies, back into the 80s and 90s before GIS was widely available. All right, now we'll quickly run through the hydrology behind SELDM, and then we can have kind of a question and answer session, or again, you can put your questions in the chat. So in SELDM, the storm flow volumes depend on precipitation, runoff, pre-storm flow, and the timing of the storm flow hydrographs. So you've seen this slide a couple times now. We're looking for our upstream load, which is the concentration times the storm flow. And the storm flow has several components for the upstream basin. And we're looking at the highway runoff load, which is the concentration in storm flow. The storm flow from the highway site is a little bit simpler. And in a later module, we'll talk about how BMPs can affect the storm flow. And then we add the storm flows together to get the downstream storm flows. So this is our schematic diagram. Again, we have our storm event statistics. The storm gets applied to the upstream basin and the highway site. The upstream basin has some pre-storm stream flows, which can also, if you're at an ephemeral stream, all the pre-storm stream flows can be 0. The upstream basin has runoff coefficient statistics, which are controlled by the imperviousness of the upstream basin. Then you have your highway site with the area of the highway and the runoff coefficient statistics, again, controlled by the imperviousness. So we add the concurrent upstream flow and highway runoff flow to get those downstream flow volumes. And again, this is just a very quick overview. If you want to dig into the details, we have the different federal highway reports, and then we have about 4 USGS reports that cover it all. They all kind of get boiled down together again in the SELDM manual, which hopefully is easy to read. I always encourage people to read the manual, but people are busy nowadays, so that's why we provide these training sessions, and we've provided the online training videos on YouTube. So, between now and when you might use the model, you can go back and refresh yourself on all the details if you need to. So we talked about SELDM has the graphical user interface with a series of forms. So we just talked about how the site and region forms provide the site properties that affect the hydrology. And then we get into our hydrology form where we're looking at the precipitation, the pre-storm stream flow for the upstream basin, and our runoff coefficients. And we'll talk about those variables right now. So SELDM uses the EPA Synoptic storm event. These precipitation statistics defined by EPA are you take hourly precipitation data and you lump them together by using this minimum inter-event time. So you have all these 1-hour pulses. So if the pulses are delayed by this minimum inter-event time in hours, then we'd have 2 separate storms. So you see these 2 hourly values down here and then a bunch of hourly values here. Because they're separated by that minimum inter-event time, we have this one event down below here and this other event down here. So we lump all those hourly pulses into individual events. So when we look over here at this storm on the right with the other minimum inter-event time, we have kind of a bunch of pulses together then we might have like a dry hour and then another pulse of rain. Because that's within this interevent time, that stray pulse out there gets lumped back into this same storm event. So we can see that would be the time in hours, and it would be the intensity in inches per hour for that storm. So we can see, you know, on the lower diagram here, all these pulses get lumped into these different events. That's how EPA defines a runoff generating event. So here's the EPA definition. So they're looking at event duration in hours, and because they use hourly data, the minimum runoff generating event is 1 hour in length. The event volume they define as a minimum of 0.1 inch of precipitation will create a runoff generating event. So any events that sum to less than 0.1 inch are not counted as a runoff generating event. Again, their definition for an inter-event time in hours is a minimum of 6 hours. And so the interval between storm event midpoints defines how many events per year that get generated over a long period of time. So our minimum for that would be 6 hours inter-event time plus 1 hour. So you'd have, if you had 2 1-hour storms, you'd have a half hour and a half hour to the midpoint. So you'd add those together. And so our minimum interval between storm events is 7 hours, according to the EPA definition. Now, we worked with EPA, and we use a lot of their stuff like the ecoregions and, you know, their definitions of a runoff generating event. So when you guys go and you're around the table with federal or state regulators or like the Fish and Wildlife, you can say, you know, SELDM is based on these EPA methods. So hopefully they'd, you know, accept them. And we got EPA and Fish and Wildlife Service involved while we were developing SELDM. So they were along for the ride. Also in Massachusetts, we got folks at the Massachusetts Department of Environmental Protection. So hopefully, you know, like I said, we've designed the process and the model to be acceptable to help support highway decision making. All right, SELDM uses the average number of storms per year to calculate a minimum number of storm events. So that depends on where you are. So when we collected the data, we tried to get stations with at least 24 years of data over a 40-year period. So we didn't want to get 24 years of data and then try and simulate 10,000 years of storm runoff from a highway. So we were shooting to get about, you know, on about 30 years of record. So if we, I guess this is kind of a nerd slide, but depending on where you are in the country, the number of events you might get depends. So if you're up in the Northwest where you have, you know, on average about 60 events, runoff generating events per year, you might get a slightly shorter long-term record. And, you know, if you're down in the in an arid area where you've got like 5 events per year, you might get a longer period because there's fewer events per year. With Monte Carlo models, you kind of want to get a kind of a critical mass, you know, a number of events so that things kind of converge to the statistics that you want. Because if when we have the manual class, you know, in-person class, we have a fun dice game where we have people roll the dice and they use a couple equations to calculate values. And until you get up to a certain number of events, the correct answer that you get can differ from, you know, by orders of magnitude from group to group. So to get the values to converge to the kind of converge towards your input statistics reliably, we have this kind of rule of thumb that we want 725 events plus 17 times the number of annual events. And for most of the country, like I said, that comes out to be about 30 years. So as I mentioned in previous presentations, that given your latitude and longitude, you can select your precipitation statistics by EPA rain zone, which are these black polygons by ecoregion, which are these pastel-colored polygons that that are discretized. Or when we went through SELDM, we went quickly to a level 2 analysis. So again, Nevada is easy to use because you have these 3 sites alone. If my site was in this area, I could pick one or the average or median of sites in this area. And to go from a region to selected sites, you want to know a little bit more about your site of interest. So perhaps one of these sites in Nevada would be representative of your site, and the other one may not. So you can look for differences and try and pick something representative. So that covers precipitation. Now we'll look at pre-storm flow. So this is a hypothetical diagram with flow on the vertical axis and runoff duration on the horizontal axis. So what we look at is down in the lower left would be a highway runoff. Hopefully you don't have any pre-storm, base flow. If not, you have to look for like illicit connections, right? So we have this short highway runoff hydrograph. In highly impervious sites, the hydrograph may last only a little bit longer than the storm event itself. For the upstream flow, we have 2 components. We have this upstream pre-storm flow, which we hold consistent throughout the storm event. So that kind of gives you your basement. And then we have this upstream runoff, which is we simulate with a triangular hydrograph, which a triangular hydrograph surprisingly does a pretty good job of accounting for the distribution of like the total volume of upstream flow through time. So you can get into a fancy curvilinear hydrograph and you get a slightly better answer, but given all the uncertainties, it's, the simpler approach is surprisingly effective. So when we look at these pre-storm flows, we can have many different values. So here's an event with a number of events. So the first, this small gray dot in the lower left on the lower blue line is a hydrograph, and then the vertical bars that come from the top would be storm event pulses. So we can see that for this first event, we have this lower hydrograph. We get a very small event. The hydrograph goes up, and then it comes back down, and we can see that it's a little bit higher than the first one, but not a lot. So then the second event is rather large, so it comes down, goes up, and as it comes down, then we have this separate event. And so the pre-storm flow for this third event would be kind of part of the tail end of the previous hydrograph. And again, you can kind of see as we go through that with this minimum time between storm events and the different hydrographs. So what happens is, storm events are usually have durations of in hours. And if you get into really big upstream basins, the storm event hydrograph can occur over days to weeks. So you can have multiple runoff events within, that kind of get stacked on top of each other. So that having the pre-storm flow that's not base flow, it could include runoff from a previous storm, helps. And usually, like I said, the small highway sites often, the timing of your drainage approximates it's a little bit longer than the timing of the precipitation versus the long hydrographs that occur during these streams. So we found that this is a pretty good representation. So when we're looking at the pre-storm flow, when you're looking at the SELDM interface, there's a number of statistics there that are mainly there to help you look for hydrologic similarity, like what are flows at one site versus flows at the other. SELDM only actually uses 4 statistics. It's looking at the average, standard deviation, and skew of the log 10 non-zero daily mean stream flow values, and it looks at the fraction of zero flows. So what's the risk of having the storm event start with a zero flow so you get much less dilution? And if you have non-zero flows, what's the statistics for that? And again, we've calculated many of these statistics for you, so you don't really have to worry about them. SELDM uses stream flow in cubic feet per second per square mile so that we use available stream flow statistics and we can apply them to upstream basins of different sites. So, if you had 10 different highways and 10 different upstream basin sizes, the chance that you're going to have available stream gauge with that exact basin size or not. And just kind of to give you some perspective, 1 cubic foot per second per mile will fill an Olympic-sized pool in about a day. So, these are a couple pictures of a full and an empty Olympic-sized pool, just to kind of give you a sense of scale. Again, with the latitude and longitude, you can select stream flow statistics by region. The ecoregions are these pink, these pastel polygons, and then the white circles are individual stream gauges that we incorporated into SELDM. We kind of tried to find more natural stream gauges so that they wouldn't be heavily affected by flows from dams and water supplies. So you can see it's easier to find a lot of stream gauges in humid areas, and there are a few gauges in the arid areas that kind of meet the criteria. We can see that, again, if we look at the middle of Nevada, there's 5 sites here. We can use the basin and range ecoregion pre-storm flow statistics, or I can pick statistics that are the average or the median of one or more of these sites in this area in the middle of Nevada, if that's where I am. And again, I kind of want to look at the statistics, look at the sizes of the basin, and pick something that would represent sites of interest. Now, recently we worked with Federal Highway and the USGS Stream Stats team, so we calculated SELDM statistics and a lot of other statistics for 18,122 US stream gauges, and they're available in Stream Stats, and they're even available in states like Nevada and Texas that don't have their own Stream Stats application. So they're available, even if you don't have Stream Stats for Basin Properties, you can go into Stream Stats and navigate your way to your state and kind of click on these basins to get the SELDM statistics. And the YouTube video on this shows you how to do that, and it also shows you how to convert the numbers in Stream Stats to the numbers that you'd enter into the SELDM form. So now we've covered the pre-storm flow. Let's talk a little bit about runoff. So the runoff coefficients are a function of the total impervious area, which is the fraction or percent of anthropogenic impervious surfaces. So SELDM uses the fraction of impervious surfaces in the interface. And again, that's roads, roofs, parking lots, etc. For the highway site, it would be the pavement. So this graph shows the runoff coefficient values with compared to total impervious area. And the white dots are all the non-highway sites we used, and I think there was about 136 of them. And then the highway sites are the gray triangles. So the regression line that we developed that relates the highway runoff coefficient statistics to the impervious fraction of the highway is that dashed blue line. And we can see, that the highway sites went down to about 25% impervious. And the other sites are, go the full range from 0 to 100% impervious. With the non-highway sites, we saw there was a break in the slope when we got to about 55% impervious. So we kind of have one relation for low impervious sites and then a different relation as the imperviousness accelerates. So a lot of people use the Schuler's NERP equation. We used a number of NERP sites here, but his equation is biased because he kind of connects the dots from 0 to 100%. So it kind of overestimates the runoff coefficients for a lot of sites. We put the Schuler NERP equation in SELDM, but we don't recommend that you use that. We recommend that you use either highway site equation, or if you're simulating, an urban area as the highway site, you use the other site equation or non-highway site equation, and use the non-highway site equation for the upstream basin. And as you click through SELDM, those choices are kind of automatically made for you, and the values are automatically calculated based on the total impervious area that you put in for your sites as you go along. Now we can see that there's can be large departures from the runoff coefficient line we have, especially down at the low end where you might have other runoff generating mechanisms than pavement, like natural imperviousness like rock outcrops, or wetlands when they're wet act like parking lots. So you can modify the default values if you know something about your site that would change the runoff coefficient. So this graph shows how with the different impervious areas, SELDM just doesn't use the same runoff coefficient for every storm. It generates a population of runoff coefficients. So if you go out to any site and you measure runoff coefficients, you're going to get it, depending on antecedent conditions and a host of other things, you're going to get different runoff coefficients. Was the site wet before or after? So this graph shows populations of runoff coefficients that get generated from an imperviousness of 0, which is the yellow line here down at the bottom. So this is the runoff coefficients that occur over a long-term simulation, and a probability scale on the horizontal axis is the probability of exceeding it. So we can see, based on the SELDM equations for this given run, that for an imperviousness of 0, you get runoff coefficients down near 0, below 1%, and near 5%. It's still very low, but your maximum runoff coefficient for a highly impervious site would, in these simulations, it looks like it was about almost 0.6. And we could see down at the low end where our imperviousness are below 50%, so the alternating colors are, increasing imperviousness by 10%. Up to about 50%, you don't get vast differences. Above 50%, you can see that there's large differences as the imperviousness increases, and that's supported by the data. So, if you're at a low impervious site, you don't perhaps need to get the perfect answer. And even at higher imperviousness, you're going to get these populations. But, as you get more and more imperviousness, you might want to do a better job of trying to define your levels. Because the runoff coefficient is often conditioned by how wet the basin was before this storm arrived. So if you have 2 large storms back to back, if your watershed is dry for that first storm, it might soak up a lot of the water, and then another storm comes along and the basin is saturated. So we looked at, what would predict the runoff coefficient, or help predict runoff coefficient. So we looked at the rank correlation to different values like the previous storm size, the time between storm. And for the upstream basin, what really predicted it, and it kind of makes sense, is what was the pre-storm stream flow. So if the pre-storm stream flow coming out of a basin is high, it usually means that the basin has been saturated by a recent event. So we found that when we look at this, the black dots are individual basins that had, I guess it was more than 7 or 10 storms. And the vertical bars, are the potential range in that value. And you can see the ones with very large differences are the ones with few data points. And as you get more and more data, the bars tighten up. So we can see that for the sites with the most storms, so therefore a better estimate of this correlation coefficient, that our correlation to pre-storm flow is about 0.7 usually. Kind of in this range, you kind of see a flat plateau here. But depending on your basin, you can make arguments for more. So if you put in this correlation coefficient, you will get, you'll condition the pre-storm flows. So your runoff coefficients will tend to be lower if your pre-storm flows are lower, and your runoff coefficients will tend to be higher if the pre-storm flow is higher. Now, they're not lockstep, but they tend together depending on the strength of your correlation. If you used a correlation of 1, they kind of would be lockstep, but higher flows would always create a higher runoff coefficient. All right, the highway is a little more complex to get at whether the basin is wet or dry. So what we did was we looked at what is the relationship between a runoff coefficient on a highway site and a runoff coefficient on a non-highway site, or a urban site versus a upstream site. So what we found was this is kind of a contour plot, which is, if you can think of as if you're looking at a hill on a map. So we have this ridge line that goes up diagonally from lower left to upper right. So what that says is when the basins are the highway site and the upstream basin have the same imperviousness, you get the maximum amount of correlation, and the correlation increases as the imperviousness of both increases. So if you had like 100% impervious upstream basin and 100% impervious highway, you'd get the highest correlation. But as you get lower and lower imperviousness, they can vary from each other, so they have less correlation. So what happens is your pre-storm flow kind of conditions your runoff coefficients for the upstream, and then the runoff coefficient upstream kind of conditions your highway runoff coefficient. So again, it kind of reflects what might happen if the basin is wetter before the current storm starts. But again, it's not lockstep. They just kind of tend to go in the same direction. All right, the next thing we want to look at is the timing of runoff from the upstream basin and the highway site. So the basin length, mean basin slope, determining the timing of runoff from the highway and upstream basin. And again, as we just described, we're looking at the area is the flux of rain. The drainage length along the main channel to the divide is affects the timing, and that 1085 mean basin slope, which is usually fairly easy to calculate, also affects the timing. So this diagram is kind of a hypothetical case study, or it's not a particular site. It's just kind of made up for demonstration purposes. So on the left, we have these hydrographs. We have in one case, we have this short, peaky hydrograph and we'll say that's a highway runoff hydrograph, and that gets us to duration 1. And then either we have let's say we put in a BMP where we stretch out that highway hydrograph to duration 2. So when we compare that to the upstream pre-storm flow and the upstream runoff, we can see that at duration 1, we only get a little bit of upstream pre-storm flow and a little bit of upstream runoff to dilute into. So if we were taking the highway runoff and diluting it into the entire upstream event, we'd kind of be cheating, right? Because a lot of the upstream water would flow by after the highway stopped flowing. But this accounting for the timing of runoff also gives us, you get added benefit by putting in a BMP that might stretch out the hydrograph. You get a lot more dilution. The old saying, dilution is the solution to pollution. So if we look at the graph on the right, it kind of gives you an idea. And again, these durations and this amount of flow are just kind of purely hypothetical. So we could see with just that short peak highway flow that